So we'll start the module 5 today, determinants, and we'll discuss about introduction and properties of the determinants. So again, these slides are picked up from the LARP 2001, Indian Institute of Technology, Madras. So you have here, we see that there are 4 uses of determinant, very important uses of determinants. There might be more of them, but we are listing here 4 very important uses of determinants. First is the test for invertibility. If the determinant of A is 0, then A is singular. That is to say that whenever A is singular, its determinant is said to be 0. If the determinant is not 0, then only it's possible to invert the A. Invert means find A inverse. The second property is the determinants of A equal the volume of a box in a n-dimensional space. If you have a n-dimensional space, then determinant of A will represent the volume of a box in the n-dimensional space. The edges of the box come from the rows of A. The edges just means sides of the box come from the rows of A. Similarly, the columns of A would also give an entirely different box with the same volume. So this is the box which is there for it, and you have the dimensions here. So naturally you can measure the length for this as root of A21 square plus A22 square plus A23 square. Similarly, the what you call length of this and length of this, if you multiply all the 3 lengths together, you'll get the volume of the box. So that volume is nothing but the determinant. We'll see later that, if you have a matrix, then by means of LU decomposition, you can reduce it to the, we already seen that it is, you can reduce it to the, echelon form or the row reduced echelon form. So reduced row echelon form, you can form them. And once you form that, then the RREF will have only the diagonal elements. So if it's a square matrix with all the columns and rows having a single pivot value, then there's always a possibility only their diagonals are present, and naturally if only the diagonals are present and all others are 0, then if you multiply the 3 or 4 whatever diagonal elements are there, then you're going to get the area, the volume of the box over there. Here volume, when we mean, it might be an n-dimensional volume here, which we are talking about. Particularly volume is considered for 3 dimension, but you can have an n-dimensional volume also. The determinants, the third one is the determinants give a formula for each pivot. From the formula, you can consider that determinant is equal to plus or minus of the product of the pivots. Plus or minus of the, if you exchange the rows and columns, there is always a possibility that you might get a minus term for a plus term. If you exchange 2 rows once, then you'll get the so to say once the what you call the positive will turn into negative, the determinant will become negative. If you change it twice, then negative of negative will become positive. So even number of times if you change, the determinant value remains same. Odd number of times you try to shift the rows and columns, then you are going to get a negative value of the what you call determinant. Okay. So the fourth one is the determinant measures the dependence of A inverse B. This is nothing but X equal to AX equal to B. If A is a square matrix, then definitely it is, if it is an invertible matrix, square and invertible matrix, then you can write X is equal to A inverse of B. So whenever you have an invertible matrix, the solution for AX equal to B will become A inverse of B. At that time, naturally, the determinant measures the dependence of A inverse of B on each element of B. So that means from the determinant, you can always, get the determinant of A. A inverse will be nothing but the determinant of A inverse will be 1 by the determinant of A. So if one particular parameter is changed in an experiment or one observation is corrected, then the influence coefficient, that means there will be change. Influence coefficient just gives change in A inverse is a ratio of the determinant. Whatever change is there in the A inverse will be the ratio of the two determinants, one before and another after the correction is made or experiment is changed. So these are the four important uses. Now the most important properties are these three, and based on this we will see the other properties are also considered. So the determinant will be defined by its three most basic properties. Determinant of the so to say the I will be equal to 1, and this I is a unit vector matrix. So the sign is reversed by the row exchange. If you exchange the row once, then the sign will get reversed. If you change it twice, it will remain same. That means even number of row exchanges will lead to no change in sign. Odd number of row exchanges will lead to the sign reversal. Then the determinant is a linear in each row separately. So that just means that the linearity property, the linear combination property of the determinants concerns with the Please disable your speaker. So determinant of I is equal to what is determinant whenever we have the determinants, the linear combination holds for each row separately. This is very much important. We'll see the elaboration of this as we go forward. So if you have a 2 by 2 determinant, let us consider the 2 by 2 determinant, which is A, B, C, D matrix. For this matrix, if you take the determinant, it will be again, mod of or determinant of A, B, C, D, that is AD minus BC. This we know very well. So the determinant of the identity matrix will be definitely 1, because the identity matrix, which is 2 by 2, will be 1, 0, 0, 1. So 1 into 1 will give you 1. Similarly, the determinant of a 3-dimensional identity matrix will give us 1, 1, 1 over here, will be 1, 1, 1 over here, and hence that will be equal to 1. The determinant changes sign when two rows are exchanged. This is what is the second property. So if you just exchange the rows, that is AB goes to the first position and CD comes to the next position, or you exchange the columns also, then it is going to become CB minus AD equal to minus of AC and B and D. So the determinant of every permutation matrix is determinant P equal to plus or minus of 1. By row exchanges, we can turn P into the identity matrix. That is, if you have a permutation matrix, by means of row exchanges, you can change it into a normal identity matrix. Each row exchange switches the sign of the determinant until we might reach determinant I is equal to 1. So the determinant of a permutation matrix is either plus 1 or minus 1. So we have seen the definition of the permutation matrix in the last class. The determinants depend linearly on the first row. This is the property which comes out. Really speaking, it comes out of every row, but we will consider first row and then you can extend it to many different rows. So in this case, when we talk about the linear combination, whenever we talk about the linear combination, you should always remember that, it will consist of both the addition of vectors, adding two vectors and multiplying a vector by a scalar. So addition of vectors is written something like this. If we can represent the first row as A plus A dash and B plus B dash, and second row as CD. Then we can separate out this, A, B, C, D and A dash, B dash, C, D. A, B, C, D over here. A dash, B dash, C, D over here, and sum of that will just correspond to the original one. So similarly, multiplying by a constant T or C, whatever you call it, the row 1, TA, TB, CD will just lead to taking out the common T over here, A, B, C, D. So this is what we are going to get. If two rows, so linearity property is very important, because we'll see that using this we might try to solve many different problems. Many different problems will get solved by this. If two rows of A are equal, then the determinant of A will be 0. If we have AB and AB, if you have in out of the, say, might be n rows, even if two rows are same, we are definitely going to get the determinant of that equal to 0. In this case, we just have two rows, and those two rows are same, then naturally AB minus BA is equal to 0. Even if you have many rows, and if two rows are same, the determinant of A will definitely turn out to be 0. You can try it with a what you call for a 3-dimensional matrix or 4-dimensional matrix or so on. Now let us see, determinant of CA is equal to C to the power n. Determinant of A is what is the corollary which is there over here, and when A is n by n, this is to be proved. Determinant of CA is equal to C to the power n determinant of A. So either you can say let or consider A is equal to this. It's a n by n matrix. Then by property 3, we can multiply just the first row, okay, by C, and all other rows we keep the same, then that will corresponds to C of determinant of A. Similarly, if you multiply only the second row and keep all the other rows same, again you'll get C of determinant of A. And similarly, you can multiply the third row only with C, and all others you keep it as it is, you are going to get a C determinant A. This you can keep on doing this. Okay, that's why we have written here so on. So under that condition, then the determinant of CA, and this C just gives us that it has to be multiplied to each of the rows of the determinant over here, then at that time, because we are multiplying with each row, for each we'll get C, 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 and for n different rows we'll get C to the power of n and determinant A. So thus we can prove this as the determinant of CA is equal to C to the power of n determinant of A. Using this, we can try to solve some of the numericals. If we have a 4 by 4 matrix, then with a determinant A is equal to half, then you need to find determinant of 2A, determinant of minus A, determinant of A square, and determinant of A inverse. So determinant of 2A will be 2 to the power of 4 into determinant of A. 2 to the power of 4 is 16, determinant of A is half. So 16 into half will become 8. Then determinant of minus A will be minus 1, that is minus 1 to the power 1, because minus A is nothing but minus 1 into A. Determinant of minus A is minus of determinant A. So then it will become minus of half. Determinant of A square will be determinant of A into A, and that can be considered as determinant of A into A is determinant of A into determinant of A. And that will be half square. And that will give us the 1 by 4 as the value of determinant of A square. Similarly, determinant of A inverse will be determinant of A whole inverse, and that will give us 1 by 2 whole inverse is equal to 2. Similarly, we can try to find out if we have a 3 by 3 matrix with determinant A is equal to minus 1, you can try to find out determinant of half of A. That will definitely become half to the power 3 determinant of A, that is minus 1 by 8. Similarly, you can go on finding all the others. The third, what you call numerical or problem which we have put over here is we can have a determinant something like this, A, B, C, D. For this determinant, you need to add row 1 of A to row 2 and then subtract row 2 from row 1, then add row 1 to row 2 and multiply row 1 by -1 to reach B. Then adding, subtracting, multiplying, adding, subtracting, and again adding is not going to change the value of the determinant. Only multiplying is going to change the value of the determinant. So if you multiply by -1, then definitely the what you call determinant also will become minus. And that is what we have here. Determinant B will be equal to this if you keep on doing all those, and that will be same thing as minus determinant of A minus of A, B, C, D. So what you have is just the change of sign. If you exchange two rows, then that will just correspond to change of sign. Then we have here, by applying row operations to produce an upper triangular U matrix, you compute the determinant of this and determinant of this. So we know by the LU decomposition, you can convert each one of this into either a upper triangular matrix or a lower triangular matrix, whatever you want, and you can get the equivalent determinant, equivalent matrix. So once you do for that matrix either the triangulation, which will correspond to finding the upper triangle or the lower triangle by means of LU decomposition or the elimination method, then if you just multiply the diagonals, whatever you get, that will just correspond to the determinant. So after finding the upper triangular form or the lower triangular form, multiply with the multiply the diagonals, then you'll get the determinant. Then the next problem will be count row exchanges to find these determinants. So we can transfer 1 and 4. We can transfer 2 and 3. Then you are going to get the identity matrix. Okay. If you transfer, exchange 1 and 4 rows and 2 and 3 rows, then you are going to get the identity matrix. So you have 2 rows exchanges. For 2 rows exchanges, it will become -1 squared, and that will become +1. So under that condition, the determinant, we know that determinant of the I, which is the what you call identity matrix, will be equal to 1, and 2 row exchanges of that will definitely lead it to +1 only, not -1 over here. Now here, if you see, this has to go above, this has to go above, and these 3 have to be shifted down. So this has to go above means that you can try to exchange this with this. So then this will come over here. Then the what you call this should be exchanged with this. Then again, this should, whatever we have over here at the 4th place should be exchanged with the 3rd one. So 3 times shifting of this what you call matrix, 3 times row exchanges will give us the determinant, the what you call identity matrix. So that will give us -1 to the power of 3, hence that will become -1. So this will be +1 and this will be -1. Similarly, find the determinant of a rank 1 matrix. So if you want to find the A, which is multiplied by this, so this is a 3 by 1 and this is a 1 by 3 matrix. If you multiply that, you have 3 rows and 1 column, and you have here 1 row and 3 column, you'll get a 3 by 3 matrix. So 1 multiplied by 2, 1 multiplied by -1, 1 multiplied by 2, then 4 multiplied by this, 4 multiplied by this, and 4 multiplied by this, then 2 multiplied by this, and 2 multiplied by this, and 2 multiplied by this. So if you see this, the rows are not linearly independent with each other because one is the multiple of the other. So under that condition, you can just try to apply again the LU decomposition, you need, or you can say the elimination method, then you'll get both the, two of the rows will become 0, 0, 0. And once one of the rows is 0, then the rank of that matrix will just turn out to be 0. And that is one of the properties which we'll see later. If one of the rows is 0 or one of the columns is 0, the determinant will be equal to 0. So the what we call determinant of this matrix will be definitely equal to 0. Then you have the upper triangular matrix. The given the so to say the what you call echelon form of the matrix over here, only the upper triangular form, upper echelon form, upper triangular echelon form, and that will be naturally here the what you call the determinant value will be just the multiplication of the diagonals, because this will have no significance because they will get multiplied with 0 and hence will become 0, whereas the diagonals will not get multiplied by 0. So if one of the diagonal elements is 0, then again this whole matrix will become 0. Here, however, that is not the case. 4 into 1 into 2 into 2 will give us the value 60. Similarly, you can find the lower triangular matrix UT corresponding to this. That means you transpose the rows into columns, then you'll get U transpose, which is the lower triangular matrix. Lower triangular matrix you are going to get, and again it is just the same multiplication of the diagonal is going to give us the determinant. Similarly, the inverse of the U can be taken, and definitely that will just kind of correspond to 1 by the determinant of the U itself. So you'll get this as 1 by 16. Then you have the fifth property, which is subtracting a multiple of one row from another row leaves the same determinant. So if you what you call subtract a multiple of one row from another row, then you are going to get the same determinant. So what you are trying to do is you have A, B, C, D. You are subtracting the first row with the multiple of the second row. That is, you are multiplying L with the second row and subtracting from the first row. Then you are going to get this. And definitely, if you try to find the determinant of this, it will be same as the original one. So it's not going to change the value of the determinant. So rule 3 says that there is a further term minus L CD CD. So you can separate this out by the rule 3 because of the linear combination property of rows, and that will just give us an extra element over here, a further term or an extra element over here, and this extra element, if you see, this matrix will give you the value, the determinant of this will be 0. If two rows are same, the value of the determinant will become same value. Hence, we'll have this quantity equal to this. So sixth is, if A has a row of zeros, then determinant of A will be 0. That means if we have one of the rows has 0 elements, then or one of the columns has 0 elements, then we'll see that the determinant of that particular matrix will be equal to 0. Okay, this is definitely true. So then we have the seventh property, which says if A is triangular, then the determinant of A is the product A11, A22, dot, 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 ANN of the diagonal entries. If the triangle A has ones along the diagonal, then the determinant of A will be equal to 1. So triangular matrix will just give us, that means if you convert this over here, AD, and this is a upper triangular matrix, this is a lower triangular matrix. So whenever we have a triangular matrix, multiplying the diagonals will just give us the determinant, because AD minus 0 into B will give AD only. Here AD minus C into 0 will give us the AD only. So this is the lower triangular, this is the upper triangular matrix. So for this, we have a proof. We have put a proof here. Suppose the diagonal entries are non-zero, then the elimination can remove all the odd diagonal entries without changing the determinant by rule 5. So we have already seen in the rule 5 that by what you call the elimination method, if we try to do the different things, that is subtraction and all that, this is the property which we might be using. That is what is elimination. And if you use that, then it's not going to change the overall value of the determinant. So if A is a lower triangular, then the steps are downward as usual. And if A is upper triangular, the last column is cleared out first using multiples of A and N. So he's just giving you the process of how a lower triangle or upper triangle can be formed. Or you can find a lower triangle and take the transpose of that, then that will give us the upper triangle form. Either way, we reach the diagonal matrix D, which is like this, and determinant of D will be A11, A22, dot, 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 ANN, determinant of I, and that is equal to, determinant of I is equal to 1, and hence we are going to get A11, A22. So what it means is that once you have this, you can take out A11 common from first row, A22 common from second row, A33 common from the third row, and ANN common from the nth row, because all other elements here and here will be equal to 0, because what we are trying to find is just a diagonalization process, which will give us the what is known as RREF form. So to find the determinant D, you apply the rule 3, factoring out A11 and then A22 and then finally ANN. That is what I told. You are taking out a common term. Leaves the identity matrix, and in the rule 1, the determinant of the identity matrix is equal to 1, and that's why from in this we are substituting 1, and all these are common values which are taken from here. So again, the problems are numericals associated with this. Find these 4x4 determinant by Gauss elimination. You can just again either convert it into the what you call upper triangle or lower triangle and just multiply the diagonals. Then you are going to get the what you call the determinant of the same. Similarly, you can do for this also. Then you have find the determinant of 4, 2, 1, 3. So again, you can find the upper and lower triangle, matrix corresponding to this by elimination method, and then find out the determinant of that. Similarly, you can do the same over here. However, the determinant of A inverse is nothing but the 1 by the determinant of A. Similarly, A minus lambda A we have, and we can try to find out apply the same rule of Gauss elimination, and then try to find the determinant of this also. Or in the normal way, you can find out for which you will get the values of. Please switch off your speakers. Don't turn on your speakers. So for which values of lambda, will this matrix be singular? So that will definitely give us, if a singular just means we'll get a value of the determinant equal to 0. We should have for what values of lambda will we get the what you call singular matrix. That means the determinant value equal to 0 is what we can find out. We can just write this 4 minus lambda into 3 minus lambda, minus of 1 into 2, that is 2, and then try to solve that equation, and you'll get the values of lambda in either of the cases. So that means if this is equal to this and this is equal to this, if this is equal to this and this is equal to this, then you will have both the rows same. When both the rows are same, then definitely that will just correspond to the singular matrix whose determinant will become 0. So for the determinant value to become 0, the condition is the what you call rows and columns. The rows should be same. The rows should be same. If two rows are same, then we'll get the determinant to be equal to 0, and that will correspond to a singular matrix. So 4 minus lambda equal to 1 will give me the value of lambda is equal to 4 minus 1. Similarly, 3 minus lambda equal to 2 will give me the value of lambda is equal to 3 minus 2. So the value of lambda will be here might be 3 and here it will be 2. And for that we will try to get the value of lambda. Similarly, we can try to apply the same rule to evaluate the determinant of A, B, and C in a similar case by converting into triangular forms. And then we can try to find out the determinant of B and determinant of C and determinant of AB. So you can see how determinant B is formed from the determinant A. So it might be that it is just the upper triangular matrix, and this is just might be the, this is what is the difference between this and this? The only difference it looks like is 9 over here and 8 over here. So under that condition, what will happen to the lower triangle matrix for C and all that? And you can try to find out the BC, AB, ATA, and CT, that is C transpose for each one of this case by converting into the triangular formation using the formula that determinant of AB is equal to determinant of A into determinant of B. Please remember that determinant of A plus B is not equal to determinant of A plus determinant of B, but determinant of A, B is equal to determinant of A into determinant of B. So we'll stop at this and we'll continue with the next slide in the next lecture because we are going out of